discuss about the analysis of unbalanced faults. We will first start with an introduction to unbalanced faults. Then we will talk about how to solve for fault currents in case of line to ground fault, in case of line to line fault, and double line to ground fault. On completion of this lesson, you should be able to develop the sequence network connections for line to line, and double line to ground faults. You should be able to solve for fault currents in case of line to ground fault, in case of line to line fault, and in case of double line to ground fault. Well, as we had discussed earlier about the types of faults, we have said the most common fault which occurs is line to ground fault. The next most common is line to ground, or double line to ground, or line to line faults. These three faults, which are much more common than the three-phase to ground faults, are basically asymmetrical faults because they create asymmetry in the current and voltage in the three phases of the system. Whereas a three-phase or a three-phase to ground fault is basically a symmetrical fault because in case of this fault, the current and voltage symmetry in the three phases are maintained. Some other type of faults, which are not short circuit faults but open circuit faults, are also present, and these are single line open faults or single phase open faults, and two phase open faults or two lines open. Now these faults again create asymmetry in current and voltage because all the three phases do not have the same symmetry of current and voltages when these faults occur. Because if you take single phase open, then there is no current in phase A if the line in phase A is open, whereas there will be currents flowing in phase B and C, and so on. Therefore, these are also asymmetrical faults. In this lesson, we will deal with the first three faults that we had talked about here. That's line to ground fault, line to ground, that's double line to ground fault, and line to line faults. These are short circuit faults, and basically when these short circuit occur, heavy currents flow in the system, and in order to protect the system we need to isolate the faults, which, as we had discussed earlier, is done by the circuit breakers, which gets the command from the protective relays. And therefore, to arrange for the settings of these protective equipment, that is the relay settings and the circuit breaker ratings, we need to compute the fault currents in the system in the event of these faults. Now we will talk about asymmetrical faults. As we have said, asymmetrical faults create unbalanced currents and voltages in the system. That is, the three-phase symmetry of current and voltages are no longer maintained. Therefore, the single phase analysis which we could do can no longer be used in this case. Should we repeat the Therefore, we need to do a three-phase analysis in this case because all the three-phase currents and voltages need to be found out, and this increases the complexity of the solution enormously. That is, solving for the three-phase system on a three-phase basis is a much complex problem, especially in case of large power systems. Now we would like to understand what happens and how we can try and solve this problem. One of the things that we understand is that power system, all the equipments are designed to operate as a balanced three-phase system. That is, under normal operating condition, the power system is always operating as a balanced three-phase system. This may not be exactly true, but more or less this condition is maintained in normal operating condition. All the generators, the transformers, the motors, all these are designed as a balanced three-phase system. So, generators will generate a balanced three-phase voltage, and if a balanced load is connected to the system, that balanced three-phase currents will be flowing through the system. As far as transmission lines are concerned, we have discussed that we do make the transmission lines symmetrical by using transposition, and therefore, in this analysis we will assume that all equipment and elements in the power system are balanced three-phase equipments, and therefore, the system or the model for all the components in the power system are same as a balanced three-phase system. Now, we have also seen in the earlier lesson that in case we have balanced three-phase systems, then if we do a symmetrical component transformation, then we will get three sequence networks, that is the positive, negative and zero sequence networks, which are independent of each other. So, when the system is a balanced three-phase system, we get three uncoupled sequence networks. It is only when the fault occurs which creates a asymmetry, then there is a connection which gets made between the three sequence networks, and the type of connection depends on the type of fault which has occurred. So, the three independent sequence networks for the system get connected at the point of fault in the manner dependent on the type of the fault. That is, dependent on what type, whether it is a line to ground fault or a double line to ground fault or a line to line fault, the connection between the sequence networks will be different, and this connection occurs only at the point of fault, whereas for the rest of the part of the system we have the sequence network as we have developed for the system. Now, in order to do the asymmetrical fault analysis, we need to make the system representation for which we make certain kind of assumptions. For the system representation, we assume that before fault system operates in balanced steady state condition. This is a valid assumption, because when the fault has not occurred, as we have said earlier, the system operates as a balanced three-phase system. Therefore, the positive, negative and zero sequence networks are uncoupled before the fault. On application of the fault, fault current will flow, and this fault current, as we have seen earlier, consists of an AC component and a DC offset current. Now, this AC component can be a subtransient current that we are looking at, which means the current just at the time of application of the fault, just after the time of application of fault, or after some time we get the transient currents, and if we are looking at a larger time frame, then we get the synchronous or the steady state current flowing in the system. Generally, as we have earlier discussed, subtransient impedances are much smaller, and therefore subtransient currents are larger, and therefore most of the time we would be interested in finding out the subtransient current, because that will determine the largest current and therefore will be useful in finding the ratings for the equipments. Now, what do we do about this DC offset current? Generally, what we do is we compute only the AC current, and for the DC offset current, what we do is we use some kind of a multiplying factor to create or to get the maximum asymmetrical fault current flowing in the system. Now, as we have said earlier, before the fault occurred, the system works as a balanced three-phase system. Therefore, pre-fault current consists of only positive sequence current, because we know that pre-fault condition the system is balanced and only the positive sequence network has the voltage sources, whereas the negative and zero sequence network do not have any voltage source, and therefore, if they are uncoupled from the positive sequence network, they are dead networks and no currents can flow in them, and therefore, only positive sequence current flows in the system under pre-fault condition, that is when the system is balanced. For rotating machines, the internal voltages, that is the voltages behind the subtransient, transient or synchronous impedance, is computed and used in the positive sequence network. This is what we had seen when we talked about the symmetrical three-phase fault analysis in lesson 26. So, we compute the internal voltage of when the load current is flowing, we compute the internal subtransient voltage and we use this voltage with the subtransient reactance as the source voltage in the positive sequence network for the rotating machine models. Then we use Thevenin's theorem and network reduction to obtain the sequence network impedance between the fault point and the reference. So, we use the network reduction methods to obtain the Thevenin's equivalent reactance or impedance between the fault point and the reference for all the three sequence networks. However, in practice we make some more assumptions, because we have said earlier that pre-fault currents are generally much smaller compared to the fault currents. So, most of the time we neglect the load impedances from the system representation. The main assumptions that we make in case of fault analysis is that pre-fault bus voltage is 1 per unit. Now, this assumption is very much valid, because under normal operating condition the bus voltages in the power system are very near equal to 1 per unit. The voltages may be of the order of 0.98 to 1.02 per unit kind of values. So, it is a valid assumption to assume that pre-fault bus voltage is 1 per unit. We make another assumption that pre-fault load currents are neglected, that is, we are assuming that before the fault occurred the system was unloaded. Now, this assumption appears to be somewhat erroneous, because certainly the system operates and it is operating under some load conditions. However, if we look at this phasor diagram, where this is the voltage phasor, then the load current phasor will be very much in phase with this voltage phasor, because the load currents will be having a power factor of the order of 0.85, 0.9 or so. So, therefore, the angle between the load current and the voltage will not be large, whereas we know that the resistance of most of the equipment in power system are much smaller than the reactance. So, basically when a fault occurs, it will be the reactive current which will be flowing, that is the current that we get when the fault occurs will be something like this. So, if on an unloaded system, if a fault occurs, the fault current will be something like this, that is, it will be lagging the voltage by almost 90 degrees. Now, if we want to see what will be the fault current when the fault occurs, when the system was working under a load IL, load current IL, then we will get that fault current by doing the phasor addition of the load current and the fault current IF. So, we will this IF, I capital F, will give us the actual load current, fault current. Therefore, if we see these two currents, we will find that these two currents will be very much in phase as well as very much equal in magnitude. In fact, if the load the fault current is, say, about 8 to 10 times larger than the load current, then the error that we get in case of neglecting this load current is only of the order of 1% or so. Therefore, in most of the cases, we do make this assumption that load current can be neglected, that is, system is working unloaded before the fault. So, pre-fault load currents are neglected. Another assumption that we make is that all sequence impedances are reactive. As I already said earlier, that for most of the equipment in power system, the reactance is much larger compared to the resistance, and therefore, the resistance value is neglected most of the time. Also, another assumption that we make is line capacitances are neglected. Well, this assumption is made mainly because the line capacitances are basically drawing the charging current, and this charging current is much smaller than the load current, even the load current, and therefore, its effect is hardly there when the fault current flows, and therefore, we can neglect this charging current, which means we can neglect the line capacitances. Now, I will take up single line to ground fault. Now, here we are showing three phases A, B and C of it may be a transmission line, maybe terminal of a equipment, maybe a bus bar. Here we are shown the fault has occurred on phase A with an impedance ZF to ground. So, this is a single line to ground fault on phase A with an impedance ZF. Now, we could have taken fault on any phase. This A, B and C has been put by us only. So, we could have put here B and C here and A here, it does not matter. So, we could take fault on any phase A, B or C. For convenience, we have taken this single line to ground fault on phase A. Now, if we remember the assumptions that we have made, there we had said that the pre-fault currents are 0. That means, the currents on phase B and C will be 0, that is IB and IC will be 0. Phase A is faulted, so there is going to be current flowing into the fault, and therefore, this is the current that we would like to find out. So, the conditions are IB and IC is equal to 0, and also for this faulted phase A, we have voltage between the fault point and ground, that is VAG is equal to ZF, the impedance, into IF, the current which is flowing through this impedance due to fault. So, ZF into IF, which is same as the current IA, because pre-fault currents are 0. So, we have another condition as VAG, which is the phase A voltage, is equal to ZF into IA. Now, if we write these conditions to find out the symmetrical component currents flowing into the fault, then we will get I0, I1, I2, the symmetrical component currents at the fault point. This is equal to the inverse of the symmetrical component transformation matrix, which is 1 by 3, 1 1 1, 1 A square, 1 A square A, this into the phase currents IA, IB and IC. Of course, here for this single line to ground fault condition, we have IB is equal to IC is equal to 0. So, these two currents IB and IC are 0. So, if we now do this matrix multiplication, we will get this as equal to 1 by 3 IA, that is 1 by 3 1 into IA plus 1 into 0 plus 1 into 0. So, this makes it 1 by 3 IA. Similarly, 1 by 3 into this 1 into IA plus A into 0 plus A square into 0. This again makes 1 by 3 IA. In the same way, we have also this I 2 is equal to 1 by 3 into 1 into IA plus A square into IB plus A into IC. So, that again gives us this IB IC being 0, this again gives us 1 by 3 IA. So, what we are getting is that at the fault point for a single line to ground fault, the 3 sequence currents I0, I1, I2 all are equal to 1 by 3 IA, that is the sequence currents are equal. From the other condition that we have for the voltage VAG is equal to ZF into IA, we can write in terms of symmetrical component. For VA, we have V0 plus V1 plus V2, that is VAG or the voltage at on phase A at the fault point is V0 plus V1 plus V2, and this is equal to ZF into IA, and IA is equal to I0 plus I1 plus I2. So, we have these two relationships, the sequence currents at the fault point I0, I1, I2 all are equal to 1 by 3 IA, and the voltage relationship V0 plus V1 plus V2 is equal to ZF into I0 plus I1 plus I2. So, here we get 3 times ZF into I1. So, V0 plus V1 plus V2 is equal to 3 times ZF into I1. So, with these conditions for the sequence currents and voltage, if we draw the sequence network, then we have the positive sequence network, which is having the voltage at the faulted point, pre-fault voltage at the faulted point Vf, since we have made an assumption that all pre-fault voltages are 1 per unit. So, this will be 1 per unit, and this Z1, the positive sequence impedance up to the fault point, this is what will be the positive sequence network. The zero sequence network will be Z0, and the voltage across this is going to be V0, the voltage across this is going to be V1. Similarly, this is the negative sequence network with Z2, the impedance. There is no voltage source for zero sequence and negative sequence network, and the voltage across the negative sequence network is V2. Now, we have V0 plus V1 plus V2 is equal to 3 times ZF into I1. Now, since this Vf is the only voltage source and I1 is the current flowing here, and I1 is equal to I0, which is equal to I2. So, it shows that we are going to have a series connection between them, and V0 plus V1 plus V2 is equal to 3 times ZF into I0 or I1. So, this is going to give us the final connection between the sequence networks. So, this is what we get. The sequence 3 sequence networks are connected in series with an impedance 3 ZF connected in series with this. So, from this network, if we need to find out the currents, the current I0 is equal to I1 is equal to I2 will be equal to the voltage Vf here divided by all the impedances which are connected in series. So, Z1 plus Z0 plus 3 ZF plus Z2. Therefore, we have here I0 is equal to I1 is equal to I2 is equal to Vf by Z0 plus Z1 plus Z2 plus 3 ZF. And what is IF? IF is equal to IA, which is equal to I0 plus I1 plus I2, which is same as 3 I1. Therefore, this is equal to 3 times Vf into Z0 plus Z1 plus Z2 plus 3 ZF, and this VF, as we have said earlier, we assume it to be 1 per unit. Now once we know this IA or IF, we can calculate the other phase currents also. IB is equal to I0 plus A square I1 plus A I2, which, since I0 is equal to I1 is equal to I2, so this can be written as 1 plus A square plus A I1, which is going to be equal to 0 only, because 1 and A square is basically lagging this by 240 degrees, and this A is lagging one angle 120 degree. Therefore, this is what we are going to get. This is showing a unit phasor, three-phase phasor, which is symmetrical and balanced. Therefore, the sum is equal to 0. Same thing for IC. IC is equal to I0 plus AI1 plus A square I2. This again comes out to 1 plus A square into I1. This term again is a balanced unit phasor. So this is 0. So this we get IB is equal to IC, which is 0. This is what we had seen earlier also when we described the condition in phase variables for a single line to ground fault. Now let's take a small example to see how this works. We have two synchronous machines connected through a three-phase transformers to the transmission line. That is, the two machines are connected to each other by means of transformers and a transmission line, as shown in the figure. The rating and the reactances of the machines and the transformers are: machine 1 and machine 2 are rated at 100 MVA 20 kV, and the direct axis subtransient reactance is equal to x1, that is positive sequence reactance, is equal to negative sequence reactance, is equal to 12% on the base, machine base. X0, the zero sequence reactance, is 5%, and the machine is connected, its neutral is grounded through a reactance of 4%. Transformer T1 and T2 are again rated at same 100 MVA 20 kV to 400 kV, that is, the line side voltage is 400 kV, whereas generator side voltage is 20 kV. The reactance of the transformer is 7% on the base of 100 MVA 400 kV, that is on the high voltage side. It will be same on the low voltage side because we are using per unit system. The line reactances are x1, x2 is equal to 15%, and x0 is equal to 50% on 100 MVA 400 kV base. So these reactances, again, since the transformer is 20 kV to 400 kV, so these are also again on the same base. So we don't need to convert them to different base. If the values are given at different bases, we need to convert them to the same base. The system is operating at normal voltage without pre-fault currents. That is, we are assuming the system to be unloaded before the fault. That is, pre-fault currents are assumed to be 0 and the voltages are 1 per unit. When a bolted, that is ZF is equal to 0, single line to ground fault occurs on phase A at bus 3. Determine the subtransient current to ground at the fault. So we have the system. This is a generator. This is the transformer T1. This is a transmission line. This is another transformer T2, and this is the motor connected. These are all having star grounded system, whereas the motor and the generators are grounded through an reactance. Now the problem says a fault occurs on bus 3 on phase A, that single line to ground fault is occurring at this point. We need to find out the fault current. Now first what we need to do is create the positive, negative and zero sequence network for the system and find out the reduced network at the fault point. So if we take the positive sequence network, then we are assuming the normal voltage, which is 1 per unit for the generator, and same is for the motor. The reactance of the generator is 12%, so J 0.12. the reactance of the transformer is 7%, that is J 0.07. The transmission line positive sequence reactance is given as 15%, that is J 0.15. The fault has occurred at this point, that is at the bus which connects the transmission line and the transformer on the motor side. So, this is the fault point, and we have this transformer reactance having 7%, that is J 0.07. This is the subtransient reactance of the motor. So, this is J 0.12, 12%. The voltage is given as 1 per unit. Since there was no current flowing initially, so the voltage angles are also assumed to be 1 per unit, 0 degrees. So, this is our positive sequence network that we have. Now, what we need to do is find out the impedance between this F and the reference. So, what we do is we will short these two voltage sources and then find the impedance between these 2 points. So, that will show that this point 19 is in parallel with point 34. So, this is what we have written, x 1 is equal to J 0.34 in parallel with J 0.19. This comes out to be, this is equal to J 0.34 into J 0.19 divided by J 0.34 plus J 0.19. That gives the reactance to be 0.1219 between fault point and the reference, and the voltage source here is 1 angle 0 degree. So, this is the reduced positive sequence network at the fault point. Similarly, we can draw the negative sequence network where everything is same except that there is no voltage sources for the generator or motor, because there are no negative sequence generating sources. So, this is a dead network, and between this fault point and the reference point we can again find out the reactance or the impedance for the negative sequence network. This again comes out to be same thing, J 0.34 in parallel with J 0.19, which gives us J 0.1219. So, this is the reduced negative sequence network for the system with respect to the fault point. Now, for zero sequence network, what we have is negative zero sequence reactance of the generator is 5%, which is J 0.05, and the grounding reactance is 4%. So, here we will get 3 times Xn. So, we have got J 0.12, 3 times 0.04. So, this will be the reactance here. For the transformer, positive, negative and zero sequence reactances are same. So, J 0.07. The transmission line zero sequence reactance is much higher, and in the problem it is given that this is equal to 0.50. This is the fault point F. Then the transformer reactance, which is again 7%, J 0.07. The machine or the motor reactance again is J 0.05, and this is the grounding reactance, 3 times the grounding reactance, to J 0.12. Again, between fault point and reference we can reduce this network. This comes out to be x 0 is equal to J 0.74 in parallel with J 0.24. This comes out to be equal to J 0.1812. So, this is going to be the zero sequence, reduced zero sequence network for the system. So, now what we have is, for a single line to ground fault, as we have seen, we have the 3 networks in series. So, this is the positive sequence network, this voltage source and the positive sequence reactance, zero sequence network, no source and the zero sequence reactance, the negative sequence network with the negative sequence reactance and no source. So, all these are connected in series. Now, this is 3 ZF is here, but here ZF is equal to 0 because the fault is a bolted fault. So, this is 0. So, what we need to do is calculate the fault current. So, first we will calculate the sequence current I0, I1, I2 all will be equal. So IF0, IF1 and IF2, which is the fault current, 0 sequence, positive sequence, negative sequence, this is equal to Vf, this is 1 angle 0 divided by x1 plus x2 plus x0 plus 3zf, this is 0. So we substitute the value. So IF1 is equal to 190 degrees. I am sorry, this should be 0 degrees. 0 degree, this is the voltage source. So 1.0 angle 0 degree, this is there, divided by x1 plus x2 plus x0. So j 0.1219 plus j 0.1219 plus j 0.1812. So this comes out to be equal to j 2.353. So this is the positive sequence current, this is same as the negative sequence current, this is same as the 0 sequence current. The total fault current IF will be equal to 3 times IF0 or IF1. So this is equal to j minus j 7.059, that is 3 times this value. So what we say is 7 per unit current flows in the fault when a single line to ground fault occurs at bus 3 of this system. Now let us take another kind of fault, that is line to line fault. Now for line to line fault, we have the fault occurring at any bus where between bus B and phase B and C are faulted through an impedance ZF. So now since we have assumed no pre-fault currents, which means IA is equal to 0. So fault conditions in phase domain are IA is equal to 0, IB is flowing like this, IC is flowing like this. So IB is equal to minus IC. So IC is equal to minus IB, and we have VBG, that is voltage from this point to ground, minus VCG, that is VBC, will be equal to ZF into IB. ZF into IB, the current flowing in this direction. So this is what is the condition for the line to line fault in the system when the line to line fault occurs on phase B and C. Of course, A, B, C are only given by us. It can be phase B or C. I can always rename it as C, B, A or whatever we like. So it basically means any two phases. So generally we put this fault on phase B and C. So this is the condition. Now we would like to transform these conditions into sequence domain. So we have sequence currents I0, I1, I2 is equal to 1 by 3 into 1 1 1 1 A square 1 A square A. This is the A inverse matrix, 1 by 3 into this, and here the condition is IA is 0, IB we have, and IC is equal to minus IB. So if we do this multiplication, what we find is this is I0 is 0, then we have I1 is equal to 1 by 3 A minus A square IB, and I2 is equal to 1 by 3 A minus A square IB. I am sorry, this should be minus here, minus 1 by 3 A minus A square IB, or it can be 1 by 3 A square minus A IB. If you see from here, I2 is equal to 1 by 3, 1 into 0, then A square into IB and minus A into IB. So this should be A square minus A into IB, or minus 1 by 3 A minus A square IB. I am sorry, this is a mistake here, it should be minus here. So and we have IA is equal to I0 plus I1 plus I2, which is equal to 0, and I1 is equal to minus I2. So this is one condition that we get, that is I1 is equal to minus I2. Now from VBG minus VCG is equal to ZF into IB, we can substitute the value. So VB we are substituting here in terms of sequence voltages, and Vc we are substituting here in terms of sequence voltages. So, Vb minus Vc is equal to Zf into Ib, and once we organize this equation, then we get a square minus a into V1 minus a square minus a into V2 is equal to Zf a square minus a into I1. So, this a square minus a will cancel out in all of them. So, V1 minus V2 is equal to Zf into I1. So, this is the other condition that we have, V1 minus V2 is equal to Zf into I1. So, we see that I0 is equal to 0, that means the 0 sequence network is open, and since there is this network, there is no voltage source. So, this V0 has no meaning. So, this network is a dead network as such. We have I2 is equal to minus I1. So, this is the positive sequence network, and this is the negative sequence network, and this current I2 is flowing in this direction and I1 is flowing in this direction. So, I2 is equal to minus I1, or I1 is equal to minus I2, and also we have this is the voltage V1 here and this is the voltage V2 here. V1 minus V2 is equal to Zf into I1. V1 minus V2 is equal to Zf into I1 current flowing here. So, Zf into I1. So, this is the sequence network connection that we get, that is positive and negative sequence network are connected across each other through an impedance Zf. So, now again we can work out for a line to line fault for the same system with the fault occurring at the same point, that is at bus 3. So, we take the same example, the positive sequence network reduced to the fault point is the same one, negative and 0 sequence network, which we have already done in the earlier example. So, now the sequence currents can be calculated as follows: If1 is equal to minus If2, and this will be equal to what? If you see here, this is Vf. So, Vf divided by Z1 plus Zf plus Z2. So, and since Zf is equal to 0, so we have If1 is equal to minus If2 is equal to Vf by Z1 plus Z2, which is 1 angle 0 divided by j 0.1219 plus j 0.1219, which comes out to be equal to If1 will come out to be equal to j minus j 4.102, and if we see what is the current IFA, IFA is equal to If1 plus If2 plus If0. Since If0 is equal to 0, therefore, IFA, that is fault current in phase A, is equal to this plus this. If we see this, then this comes out to be 0, because this is the value that we will get for If1 and If2 is negative of that. So, this is equal to 0. Ifb is equal to a square If1 plus a If1 plus a If2 plus If0. If0 is 0, therefore, this is equal to minus j 4.102 minus 0.5 minus j 0.866, this is a square, and then this is a into If2, this is If2, I am sorry. So, this is equal to this. So, when we do add this up, we will get this as equal to minus 7.105 plus j 0.0, and since Ifc is equal to minus Ifb, therefore, this is equal to 7.105 per unit. So, we can calculate the phase currents in phase A, B and C for the fault, line to line fault, which has occurred between phase B and C. The fault currents, as we see here, are 7.105 per unit, or 7 times the rated current on the system. Next, we will take double line to ground fault. Now, here what the conditions are again very similar to the line to line fault that we had, except that these two lines are faulted to the ground through an impedance ZF. Now, again here pre-fault conditions, the currents are pre-fault currents are 0. So, Ia is equal to 0. Now, Vb is equal to Vc because these are shorted, and this will be equal to ZF into If. And what will be If? If will be this current Ib and this current Ic. So, the current here is going to be sum of these two currents. So, If is equal to Ib plus Ic. So, fault conditions in phase domain, Ia is equal to 0, Vcg is equal to Vbg, that is Vc is equal to Vb, and Vbg is equal to ZF into Ib plus Ic. So, this voltage Vb or Vc is equal to ZF into Ib plus Ic, which is same as If. Now, again saying Ia is equal to 0 means I0 plus I1 plus I2 is equal to 0. This condition that we get. The other one for the voltage we can write V0, V1, V2 is equal to, this is A inverse into VA, VB, Vc. Now, Vc is equal to Vb, so we have substituted it like this. Now, from here we get V0 plus A V1 plus A square V2 is equal to V0 plus A square V1 plus A V2, which tells us that V1 is equal to V2. Okay. So, and Vb is equal to ZF into Ib plus Ic. So, again substituting the values. So, Vb we are writing plus ZF into Ib plus Ic, and then again taking help of V1 is equal to V2 and A square plus A is plus 1 is equal to 0, or A square plus A is equal to minus 1. We will get finally on organizing this, all these terms in this as V0 minus V1 is equal to ZF into 2 I0 minus I1 minus I2, and this we can write as ZF into 2 I0 minus I1 plus I2, like here, which is same as ZF into 2 I0 minus I0, because we have I0 plus I1 plus I2 is equal to 0. So, I1 plus I2 is equal to minus I0. This we get from, this we get from here, I1 plus I2 is equal to minus I0. So, we have this comes out to be 3 ZF into I0. So, V0 minus V1 is equal to 3 ZF into I0. V1 is equal to V2, and I0 plus I1 plus I2 is equal to 0. So, these are the conditions that we have got, which tells us the sequence network connections are going to be like this. V1 is this is the positive sequence network, Vf is the voltage source, Z1 is the impedance, and V1 is the voltage between the fault point and the reference. We have the negative sequence network, which is only having Z2, no source, and the voltage across this is equal to V2. So, V1 is equal to V2. So, this will be connected across this, and then we have, this is the value V1, V0 minus V1 is equal to 3 ZF into I0. So, V0 is, this is Z0 and the voltage across this is V0. So, V0 minus V1 is equal to 3 ZF into I0. So, 3 ZF into I0. So, this current is flowing like this, I0. So, 3 ZF into I0 is the drop here. So, V0 minus V1 is equal to 3 ZF I0. This condition is put here. So, this is the final network that we get, interconnected sequence network for double line to ground fault. Again, we will take same example, except that in this case we have taken the fault to occur at bus 4. So, again the fault is with ZF is equal to 0, double line to ground fault at bus 4. So, what we need to do is we need to compute the sequence network at the fault point. So, we have drawn the positive sequence network, which is same as what we have drawn earlier, except that the fault point is here. So, now we need to find out the reduced network between fault and reference, which if we do, which comes out to be J 0.0928, because this part is, this impedance is around J 0.41, this impedance J 0.12, they are in parallel. So, this on reduction finally comes out to be this much. Similarly, negative sequence network, again since the impedances are same, so the value of x2 is also same, that is J 0.0928. Now, for 0 sequence, again we can calculate the value here. Now, this comes out to be, the network is same except that the fault point is here. So, we add these impedance, this comes out to be 0.81. So, J 0.81, and this is 0.17. So, J 0.17 in parallel, this comes out to be J 0.1405. So, this is the network here. Now, we connect these networks as we have shown, V1 V2 in parallel and V0, and that is Z0 and 3ZF in series connected in parallel with that. So, this is what we get, VF. This is the positive sequence impedance, this is the negative sequence impedance, this is 3ZF, is ZF is 0. So, this is 0, and this is the 0 sequence impedance. So, interconnected sequence network will be like this. We can get the positive sequence current as, if you see here, this will be this VF divided by the impedance, this impedance plus these two impedances in parallel. So, that is what we have done, Z1 plus Z1 Z0, that is, it should be Z2 Z0, Z2 is same as Z1. So, it is Z2 Z0 as Z1 Z0 divided by Z1 plus Z0. So, this is coming out to be equal to J minus J 6.747. Similarly, we can calculate IF2, which will be, again, if we look at this diagram, this is I1, this gets divided into these two parts, right, and the part flowing in this is going to be inversely proportional to this impedance and the sum of these two impedances. So, that is what we have got here, IF1 minus IF1 into Z0 divided by Z2 plus Z0. When we do that, we get this as J 4.06 per unit. Similarly, IF0 can be computed as minus IF1 into Z2 by Z2 plus Z0. So, substituting values, this comes out to be J 2.684 per unit, and once we have got these positive, negative and 0 sequence currents at the fault point, we can calculate the phase A current, that is I0 FA plus I1 FA plus I2 FA, positive, negative and 0 sequence fault currents. This, when we add up, this comes out to be 0. This is what we had seen in the very beginning, that there is no current flowing through phase A. IFB, again we substitute the values and then we calculate, this comes out to be 10.188 with an angle of 156.7 degrees. Similarly, IFC, after substituting the values, comes out to be again 10.188 with an angle of 23.284, which shows the values for these two currents. So, we know the fault currents in all the three phases. So, with this we will stop today. In the next class we will talk about some other asymmetrical faults, that is the open circuit faults, and then we will take up some example and we will see how we do this fault analysis for large power systems. What are the problems that we have to face when we work it out for large power systems. Thank you. Welcome to lesson 29 on power system analysis. In this lesson, we will continue with unbalanced fault analysis. The symmetrical faults that we were considering in the previous lectures were the short circuits. In this lecture, we will consider the open circuit faults. So, here we will start with an introduction, then we will discuss one line open fault and then two line open fault, and after that we will discuss a little about fault analysis for large power systems. Well, on completion of this lesson, you should be able to develop sequence network connections for open circuit faults, and you should be able to explain the objectives of fault analysis for large power systems. As we discussed in the previous lesson, there are different kinds of faults which occur in power system, such as line to ground fault or line to ground faults and line to line faults. These are asymmetrical faults. Similarly, three phase to ground faults, there is a symmetrical fault. All these faults are basically short circuit faults, whereas we have other types of faults which are basically open circuit faults, like a single phase open, that is one line gets open or two line gets open. In both these cases, the fault again is an asymmetrical fault, because the voltage and currents in all the three phases are not balanced or symmetrical. Now, when we one question which comes to mind is, we can understand studying the short circuit faults, because in case of short circuit, heavy currents are going to flow in the circuit, and we need to protect our equipment from damage because of this heavy current. What happens in case of open circuit faults? Well, open circuit faults in most of the cases will lead to over voltages, and that is why we need to study them, because these over voltages can sometimes cause insulation failure and thereby resulting in a short circuit. So, we need to study these open circuit faults also to make sure that our system design for insulation can take care of the over voltages caused by the open circuit faults. So, that is, if you see the system, we can define this is a n bus power system in which we have taken this bus Q at which the fault has occurred. The fault impedance is ZF, and the ABC phase voltages are shown here for the bus Q. So, with this we end today. In the next lesson, we will talk about how to develop an algorithm for short circuit studies on large power systems. Thank you very much.